So why don't you guys try this one out yourself, just for a little bit. Give you maybe 3 minutes, see how far you can get on this sucker. Give you, or you didn't ask for. I have extra calculators if you need them. Whoa. Wait, why are you talking to other people? Pretend this is the test. Oh. Pretend this is the test. Let's see how you would do. The test is next class. This is very similar to one of the questions on the test. See how you would do. you guys get that? Pretty straightforward. Obviously on the test, could be a different hydrocarbon, right? And different amount that you start with. But start with the balanced chemical equation and work through this guy. Yes.
Do we have to do all of that? Or temperature just go fine, so when we said that whole thing,
If it was this easy, yeah. If it was this easy, sure. Any questions on that? Anyone not get this? Oh, cool. Okay. Good to know. Let's try another one. What's the numerical rate of fusion between argon and krypton? Did you guys get that? Make sense to everyone? Yes, sir.
when we write like the answer, are we just writing 1.448 times, or do we have to write like the whole
Let me go back and hold on. Let's see how I have the test. What is the numerical rate of fusion difference between Yeah, I just like that. It doesn't, you don't have to fill in a sentence. Yes,
So it's always the bigger one.
the larger molar mass, yes. Yes,
But when I did it, I got.
okay, so you do 83.8 divided by 39.95 and hit equals, and then put it under the radical. So don't do radical. Don't do it here, because you can simplify the radical first. Got another slide for you. What's this for? We only saw it briefly in a video. Remember that day we watched 3 videos about the same thing?
Oh,
it's like the bad experience. Oh.
So what is this table? You'll see it on your test. What are you going to use it for?
us sending.
I'm sorry? So this is temperature, right? You're not going to use this guy. This is in Fahrenheit. What's KPA? And what's torr? And what's ATM? Pressure. So do you remember on a video where they looked up a value on a table? Okay. Well, it was day 5 where you had to watch 3 videos on how to determine R. How to determine R, right? We watched the first guy, he's at university. Remember this dude? Yeah, and he got the barometric pressure, he said, from your TA or whatever, you'll get your barometric pressure because they were collecting, what gas did they collect? Hydrogen gas, right? Collected hydrogen gas. And then we watched this guy. He stuck his, yeah, he just kind of winged it. Just kind of winged it. Then we watched this guy. Don't think it was TED Ed. A little more professional though, and used, yeah, used a udiometer to figure it out and actually use the table. And this was the only one that used the vapor pressure of water table. Remember, when you collect gas over water, you got to use Dalton's law of partial pressures and remove the evaporative pressure of water to find the total pressure. Does that make sense to you guys? So this is the vapor pressure of water at a specific temperature. So if it's 20 degrees, then you come over and you can either pick this for KPA or you could pick this for ATM. Stay away from torr unless it's in torr, but I don't think I use torr. Or it might be at 25 degrees, right? That's how you read this table. What? And you need to know what the table's for. Remember, if you're collecting gas, so here's your water level. Let's put your water level here too. And you have gas particles up here. Let's say the tube has bubbled up all your hydrogen. The different ways it was done, whether it was through a stopper or a tube. Just give me a second, please. So you've bubbled up and you have a bunch of hydrogen gas in here, and it's creating its own pressure because at a temperature, it has enough kinetic energy to bounce around, right? But also, if this is water, at the surface here, you have some water molecules evaporating, right? So you're collecting it over water. So you also have the vapor pressure of the water molecules. So if you're looking for the pressure of the hydrogen, you have to take into account the pressure of the water molecules too, right? So these two added together give you the total pressure. So that's why I'm saying you have to use Dalton's law and subtract the partial pressure when you collect gas over water. Make more sense? So. So that's what that's for. Now, let's see, what are your other questions on the test? I thought those would be the most challenging one. Oh. Calculate the density. Calculate density of nitrogen gas at 150 degrees Celsius and 99.9 kPa. you guys get that? For density? Yeah? Pretty straightforward. What was your final density? Anyone? You're gonna make me do it? Well, then I won't go over any more problems.
0.80.
I'm sorry?
Uh,
0.796. But, okay, so, but you guys 0.796?
Yeah.
And that would be, what are the units? Grams per liter, and then to put that into 2 sig figs. 80. Right, these are the 2 sig figs. And it's still grams per liter. Now, how about this one? How many grams of chlorine gas are there in a 50-liter container at 22 degrees Celsius and 825 torr? This is a pretty classic question. Are you done? Most missed question on these kind is not converting to grams. Right? So make sure you know you're not done. Yes.
Do you have to convert from 40 to?
Yes, because this is in either ATM or kilopascals. And you wouldn't want to convert from torr to kilopascals because that's 2 steps. Doesn't make any sense. But yeah, you do not know the ideal gas constant for torr. How do you go from moles to grams? So what is 1 mole of, what is this, chlorine? 70.90 grams. 3545. So you get 159. Oh. 159.525 And that'd be grams, but we need it in how many sig figs? 3 sig figs, and this 5 bumps this up. So 160 is not 3 sig figs. But 1.6 times 10 to the second grams of Cl2 is 3 sig figs. Yes, 160 dot. Like that. If it's as clear as this dot is right here. Yeah, I will be flexible with that one. Especially since sometimes you guys screw up and make remember the base number has to be less than 10 and greater than 1. So sometimes you put 16 and you get it wrong. 16.0 times 10 to the first is not the same. I mean, it's the same, but it's not proper scientific notation. What do you think? You can do that one? Then straight up total one. 6 atmosphere and 8 liters compressed to 2 liters. What's the new pressure? So boil. Yeah, these are straight up gas law problems. Straight up gas law problems, except for what's the difference between real and ideal gases? Well, did you have to write it concisely? So that's a question. Says what is the difference between real and ideal gases? So stick with the question. Don't then talk about how we can use ideal ones to represent real. Don't stick with just the question. Stay on target, right? Just give me the difference between real and ideal gases. The other one is, what are the 5 postulates of the kinetic, molecular theory? There we go. And then on a few questions, I ask, what is the pressure? So just a straight up Boyle's law question. What is the pressure? And then I leave you a space, ATM, kPa, millimeters of mercury, and torr. So you have to do a Boyle's law, but then you also have to be able to convert your answer into all 4. So I do that with, I do that with pressure. I do that with temperature, basically Kelvin to Celsius, and I do that with volume. So I do that with volume. You got a blank liter, you got a blank milliliter, you got a blank centimeter cubed, a blank decimeter cubed. So big thing to remember with these, they should all have the same sig figs. Right? Even though you convert, they need to all have the same sig figs. So that's about all I got. Is that a question or a stretch? It's a stretch. It's a good stretch. Do you feel confident about this test? Yes.
I need to convert to Fahrenheit.
No. No. Nope, nope, nope. Nope, nope, nope. Any other questions? Now, I have it printed, well, actually, let me just show you what it looks like. Let me zoom out a little. You. Oh. Basically, I have it printed like this. So 1, 2, 3, 4, 5. So I left you like this much space. And then on the other side, there's your table. That you have to use with this data. What's the difference between ideal? What's this? So I have it printed like that. Do you think that's enough space, or should you guys bring scratch paper? Okay, so. Then you might want to, or I'll provide scratch paper. Oh, I could also make a copy stapled to a blank piece of paper. And then you just tear off the back.
So how many questions are there?
20. And you already know a couple of them, right? So you know this one, you know this one. Oh, you know this one, this one. So that's 4 out of the 20. You already know. Oh, 5 out of the 20, except for it could be different. 6 out of the 20. Oh, yeah. And then the other ones, they're straight up from your worksheet. They're straight up from the worksheets. They're really Boyles, Charles, Gay-Lussac's. They're just word problems, word questions. Yes. What? You don't need to know the names. Don't need to know the names. But you want to show your work the way we've been doing. Yes.
Can you go over the question with the table? Like the top?
The question with the table. So it's going to be different for each version, but basically a student is tasked with calculating R, which is what the 3 labs collects hydrogen over water, uses 0.0190 grams of magnesium. So I give you a mass of magnesium. Let me go to this. So it's just describing a student, and I give you grams of magnesium. The water temperature is, so I'll give you the temperature, let's say 298. Barometric pressure is, so you're given the pressure, let's say 1 atmosphere. The volume of the gas collected was 84.7 milliliters. And then it says, what is the student's experimental error? what's the student's experimental error? So basically you can plug in any gram here, but I give you, remember it was a small amount. So they're all going to be, like 1.5, 1.8, 1.9. They're all going to be small amounts of magnesium. And then you have to remember the equation, right? You're putting magnesium metal with hydrochloric acid to yield hydrogen gas and magnesium chloride. But what's really important is the ratio between magnesium and hydrogen gas, right? So it's a 1-to-1 mole ratio. So basically you'll turn your magnesium into moles, right? So you'll times this by the molar mass, which would be grams over mole. And then times the mole ratio, mole over mole, right? And then to get to here, I wish 298 wasn't there. So then you'll have moles of hydrogen. Moles of hydrogen. So then you can use PV equals nRT to solve for volume. Right. To solve for volume and compare, because you got moles. What volume should you get? What volume did you get? And then the student's experimental error, since it says calculating R, this is the volume. You're going to have to, if this is atmospheric pressure, remember this is P total. So you'll look up on your chart for the pressure of water, right? And you'll solve for here, and that will give you the pressure of hydrogen, right? Because this is given to you, you look on the table for this and you solve for that. That's the pressure of the hydrogen inside the container. Just makes sense to you what it's like. So the numbers could be different, but the student's experimental error, you're gonna remember that is theoretical minus experimental divided by theoretical absolute value times 100. And our theoretical, if you're given, so this one has barometric pressure, it's an ATM. So if you're given ATM, your theoretical is 0.0821, right? This is the R value. You're comparing the student's R value versus the one that you're given, right? This is in theory what R should be. And if in your problem you're given kilopascals, then you can either convert or compare it to 8.314. Right, so this, what's the student's experimental error? You're comparing R's. Compare R's. Basically the ones you use, and then the ones this amount and this amount give at this temperature give you. And that temperature and this pressure. Do you think you should try one? Okay. So, okay, I'll just use this one here. And then I'll put the table back up. Ooh. Okay, so collects hydrogen over water, uses 0.019 grams of magnesium. Water temperature is 25.0 degrees Celsius. Oh, this is a 0 right here. Just for your sig figs. Barometric pressure is 0.985 ATM. And the volume of the gas collected was 84.7 milliliters. So what you're gonna wanna do is this becomes 0.0847 liters, because we're using Pivnert, right? That can stay the way it is. This becomes 298 Kelvin. And then 0.019 divided by 4.1. This, where are you? This becomes 7.8 times 10 to the minus 4 moles of mg. What? What?
Isn't that 360?
2 times 10 to the minus 4th mole mg, which also is mole of H2, because it's a 1-to-1 mole ratio. So experimentally, to solve for R, switch to this one. R equals PV over NT. So to find the pressure, we're going to do the atmospheric pressure as the total, 0.985 ATM. That's total. That equals, we're going to do the water pressure plus the pressure inside the tube to find the water pressure. It's at 25 degrees. Do I want to use this guy or this guy? I want to use the ATM, so 0.0313. So let's go back. Oh, here, where are you? 0.0313. This is ATM. So what is the pressure for the hydrogen? 95 minus 0.954 ATM. And the volume is here, this volume here. So 0.0847 liters. Mole is 7.82 times 10 to the minus 4 mole. And temperature is 298 Kelvin. Does that make sense to everyone? Have I lost anyone? So we're just gathering information from multiple places. And then calculator work. 954 times 0.087 equals divided by 7.824 equals R equals 0.347. And none of the units cancel, so that's ATM times liter times mole times Kelvin. That makes sense to everyone?
I got a 0.348.
Okay. Okay, so. Okay. So is this the answer? Nope. Nope. Because it's asking what's the student's percent error, right? So with ATM, 0.0821 minus 0.347 absolute value divided by 0.0821 10 times 100. 0.821. 26.4 divided by 0.0821. And wow. 322% error. Oh, 323% error. What do you think? You might want to watch that last video, the third video again. The third video, because then if you watch it to the end, it shows you all the different stuff and how to do the sig figs and everything. I'm sorry? Okay, that's so video lab comparison. So that would be day 5. Is there a better way I could organize this? Anyone? Make it easier to find stuff? Well, if you think of something, let me know. How do your other teachers organize it? Do they do a folder a day? Some do? Yeah, yeah.
What my teachers do is, instead of doing, they'll usually, sometimes they'll label it by day, but usually, some of my teachers will just organize it different, like, materials, worksheets, tests, and like stuff, and so you, or like, and so you go, and sometimes inside those mini folders will be organized individually. So they do this, so like you want to find just the resources from day 5, you just go into resources folders, look for the thing we would do.
But you still have to know that it was day 5 resources.
Well, oftentimes see like, we'll say like day 5, whatever it is, like the name of the material or the file name says what it is, also be like day 5.
Okay. So this would be better if it was like calculating our videos.
I like the way it is. I think it just generally depends on what materials this is.
I wish teachers could see other teachers' Schoologies.
I don't show here.
So different from class to class.
But you know, teachers, students have had to do that since the beginning of time. Teachers are different and they run their classrooms different, so they would run their Schoologies different. And that's good, because then you become flexible for different jobs
I miss classroom.
and adaptable. Yeah.
When Mr.
With 20
Brown-
million resources online, how do you classroom as compared to school?
Yeah, no, but.
When Mr. Brown wrote